Okay, so we have a lecture 25 Matroid. All right, so in the previous lecture we defined the matroid, right? The matroid as a set system satisfying three axioms, right? So the set system is it's a, right? So you have a finite set E and set of subsets of I, a set of subsets I of set I of subsets of E satisfying these three axioms, right? So the empty set is in I, and whenever you have something in I, then any subset is in I. And if you have two sets in I, then and if one has a less number of elements than the other, then you can extend the smaller one by adding some element from a bigger one. And we say that something, a set contained in this set I is independent. Right? So this I is a collection of independent sets. And this is precisely like the linear independent vectors. And in fact, when you have a set of vectors, which are then collection of all linearly independent vectors will form a matroid, and those matroids are called vector matroid. And if you have a graph, collection of all edge sets, including no cycles of the graph, form a matroid, and this is called the cycle matroid. Right? And something is independent in M if it's in the member of I. It's dependent if it's not independent. All right. Yeah. So let me continue. So we say X is a circuit of a matroid M if X is minimally dependent. So what are the circuits? So in a vector matroid, circuits are the set of vectors, so that whenever you delete one, then remaining are linearly independent. Right? So for instance, in the plane, circuits are, for instance, any three vectors, right? Any three generic vectors on a plane will form a circuit, because if I remove anything, then the remaining are linearly independent, but all three are dependent. Right. But also two vectors pointing the same directions form a circuit, because one of them, if I only have one of them, it's linearly independent, but if I have both of them, they're dependent. Right? Remember, what is minimally dependent? So this means that X is dependent, but every proper subset of X is independent. That's what it means to be minimally dependent. Now, here's a theorem. Let M be a matroid. Let C be the set of all circuits of M. Then C satisfies the following three axioms. So first of all, empty set is never a circuit. Why? Because empty set is independent. Second axiom is, if you have two circuits where one is a subset of the other, then they are actually equal. Because we chose minimally minimally dependent set, so no proper subset is dependent. So C1, C2 are trivial. Just from I1 and I2 and the definition of circuits. So the most interesting part is the last one. If C, D are circuits and they are distinct and you have some elements in this intersection, then there is another circuit such that this one is a subset of C union D minus E. So in the picture, in the graph, oh wait, yes, I forgot to mention the circuits of cycle matroid correspond to the cycles of G, right? Because when you have a cycle, then if you delete any edge, then you no longer have a cycle, and so therefore it's independent set. And the cycle itself is dependent. So cycles are precisely the minimally dependent set. So those are circuits of the matroid. Now, let's prove why. Okay. Right. So I1 obviously implies C1, and right, and by the definition of circuit, C2 is trivial. Now it remains to prove the C3. Wait, what is the meaning of C3? So if this is a circuit C and this is circuit D and there's an edge element E, then what it's asking is find the circuit here, right? That's right. But we knew that, oh yeah, there's a circuit. So this is in the case of graphs. How do we find it? So suppose not. Suppose C union D minus F does not contain any circuit. So C union, what does that mean? That means C union D minus E is dependent. No, independent. Why? Because if it's dependent, then it must contain minimally dependent set. Because empty set is independent. Right? So since it doesn't contain any circuit, that's not possible. So this is independent. So this is in I. Now, here's a C, here's a D. Okay. And let F be the element of D minus C. By C2, such an F exists. Right? D cannot be a proper subset. So you can find an element F. All right. Now choose a maximal independent subset I of C union D containing D minus F. Why do I say that? Well, note that D minus F is independent. So such a maximal independent set exists. Right. Now, I is such a set. So I is a maximal independent set containing D minus F, and it's a subset of C union D. And by I3, all such subsets have the same size, right? But anyway, let me let me look it up. So F cannot be in I because D minus F union F is dependent, right? And C is not in I, right? Because C is dependent. So let's compare that. So to compare the size of I and C union D minus E. So I doesn't contain F, right? So F is not in I, and I doesn't contain C, so some element of C is not in I. So therefore, the size of I is strictly less than C union D minus C union D minus E, right? But both are independent, right? So therefore, by I3, there is X in C union D minus E minus I such that I union X is independent. Now, and X cannot be F, right? Because I contains D minus F. So if I add an F, then it's dependent. So X has to be inside C minus D. Wait, but that's weird. Okay. Contradiction. Well, actually, it doesn't matter. Okay, let me remove this. This is contradiction because I was a maximal independent subset of C union D minus F containing D minus D minus F, right? So that's it. So the list of circuits satisfy these three properties. Whenever you have a matroid, then circuits satisfy all three. Now, what's funny is the converse also is true. So let C be a set of subsets of a finite set E satisfying C1, C2, and C3. Now, this defines a matroid. How do we define a matroid? Let I be a set of subsets of E such that X does not contain any member of C as a subset. Okay, then we claim that E I is a matroid. So this is an example of alternative definitions of matroid. And indeed, there are more than 100 different definitions of matroid, which are all equivalent. So sometimes we use independent set, sometimes we use circuit, and depending on the context. And sometimes it's easier to work with the circuit, sometimes it's easier to work with independent set. And I will describe some of them in this lecture. And in many cases, the proofs are straightforward. Sometimes proofs could be quite tricky. This kind is proof is not too bad, right? So how do we define a matroid? Like, how do we define independent set? Well, independent sets are the sets which does not contain any circuits. All right. So how about I1? Okay, let me show you the I1. Right. Okay. So I1 empty set. Empty set is independent because C1 hold, right? Empty set is not a circuit. What about I2? I2 is trivial by definition. Definition of I. Now what's left is I3. All right. Now, how do we prove I3? I3, I'm talking about X and Y. So suppose I3 fails. Choose a count example. XY with minimum X minus Y. Okay, among all count examples, I choose the one with this side as small as possible. Right? And clearly, X minus Y is non-empty. Because if X minus Y is empty, then X is subset of Y, and by I2, then it's trivial, because any subset of Y is independent, so X plus any single elements will be independent. Okay, so if X minus Y has at least 2 elements, then let's choose some element in X minus Y and let X prime be X minus E, right? And then by the assumption on this pair, there is Y in the, let's not say YF, in Y minus X. Okay, not only F, but okay, let me see. There are F and G such that X prime union F G is independent. Is in I. Why? Because when I deleted this set, X prime is smaller than Y, but X prime plus 1 is still smaller than Y, right? So I can apply I3 twice, right? In both cases. So this minus Y is still smaller than X minus Y. So this pair, these two pair the pair of x prime union f and y is still not a count example. Remember, we chose count example with the minimum x minus y, so this is fine. This is no longer count example, so it can apply I3, so this is independent. Okay, so now what's happening? So I had x prime. No, initially I had x prime, no x, and x prime union fg. This is not a count example, right? Because x minus x prime union fg is still under, it's 1. So that means there is like, so that means by I3 x union f or x union g is in I, right? So this kills the case when x minus y has size 2 or more. Thus, we may assume x minus y has only single elements. So there's only one element. Now, by taking a subset of y, we may assume that y minus x has size 2. Okay, so let fg be the elements of y minus x. So this is E. Okay, now let's look at the circuits. By the assumption x union f is independent and x union, no, it's dependent. So there are circuits C and D, which is subset of, such that C is a subset of x in subset of x union f. This is a subset of x union G. And C is not a subset of x, so C must contain f, and D must contain G. Right? And E must be contained in both of them. Why? Because if C doesn't contain E, then C is a subset of Y. But Y is independent, so there's no circuit. So C intersection D contains E. So by C3, there is F, which is a C union D, subset of C union D minus E. Right. There is a circuit. Should I say circuit? In C. Alright, so what does that mean? Now, but then F is a subset of Y, contradicting the assumption. That Y is independent. Okay, so that's the proof. So you see that I1, I2, I3, these independent set axioms are equivalent to C1, C2, C3 for matroid. And both defines a matroid. And there are many more things. Okay, so so far we define independent sets. Yeah, independent sets and circuits. So next thing we define are the bases. So a base of a matroid as a maximal independent set. Okay, and it's like a basis in a linear algebra. So a basis of vector space is a set of vectors which span everything, and it's linearly independent. So it's the same. Now here's one observation. So let M be a matroid. Let B be a the set of all bases of M, then B satisfies the following. First of all, set of bases is never empty. You must have at least one base, because empty set is independent. So you start from an empty set, you can grow it. At some point, it will hit the maximal independent set. This is because E is finite set. All right. Now, if you have two matroid, B1, B2, two bases, where X is in the B1 minus B2, then there is Y in B2 minus B1, B1 minus X union Y is in B. So this second axiom is called the basis exchange axiom. The base exchange axiom. And this is the non-trivial part, right? So if you have two bases, and if you have one element, and you have some element in B1 minus B2, then you can delete that element and extend it by some other element, right? So let's see why this is true. B1 is true by I1, right? That's trivial. How about B2? All right. Again, it should be. All right. Okay. By I3, I know that the size of B1 is equal to size of B2. So all maximal sets, all maximal independent sets have the same size. Now, suppose that B1 minus X union Y right is dependent for all Y in B2 minus B1. What does that mean? Yeah, so let X be in B1 minus B2. If that's dependent, No, I probably I don't have to. Okay, yeah, it should be a lot easier. Note that b1 minus x is independent. Now we compare b1 minus x and b2, and so apply I3. So both of these two sets are independent sets. So there is y in b2 minus b1 minus x, which is actually equal to b2 minus b1, such that b1 minus x union y is independent. Okay, and since all maximal independent subsets have the same size by I3, b1 minus x union y is a base. That's it. Right? So that proves that maximum independent sets satisfies these two axioms. Now again, we prove the converse. Let B be a set of subsets of a finite set E satisfy B1 and B2. Now we claim that then the how do we define a matroid when you're given a basis? Let I be a set of subsets of E such that X is a subset of Y for some Y in the base. Then EI is a matroid. So we need to prove I1, I2, I3. So I1 is implied by B1, right? We know that set of bases contain, there is at least one base, and then all subsets of bases, the base is also independent, so therefore empty set is independent. And I2 is trivial by definition, so it's enough to prove I3. Okay. Now, suppose not. Let me show you I3. So where's I3? Okay. Suppose I3 is force. All right. Then there's an xy in I, size of x is less than size of y, and for all y in y minus x, x union y is not in I. All right. Now, we need to prove that this is not the case. Right? So, let B1, bx maybe, let bx be the member of B and by be a member of B, such that x is a subset of bx and y is a subset of by. Because these are independent, this is the case. If bx intersection y minus x is non-empty, then we are done, right? Then there is y in bx minus x. Okay, so I don't have to say, oh yeah, let me still say, oh yes, bx intersection y minus x such that b, right, okay, then let, and this implies that x union y is independent. Contradiction to our assumption that xy is a counterexample. The pair xy is a counterexample. So bx does not contain any vector, any elements in y minus x. Okay, so here's an x, here's y, and here's a bx, right, and the by, maybe by looks like this. All right, I mean they have the same size. My picture is big wrong. Now among all these pairs of bases bx and by, choose bx by so that something is minimized. Okay, I will add the condition later. Let me just put a blank. So after completing the proof, we will fill in the correct conditions. So what I'm going to do is the trade between x and bx and by. bx does not contain any element of y. Okay, so where is bx? This is bx. Maybe it's okay. Then let y be in y minus x. By b2 there, which is also in, this is also in by, there is an element in bx such that by minus y and add something is a base, right? I can delete y from by and add somebody in bx minus by, right? Now let this one to be by prime. No, yeah, by prime. Okay. That's not a good direction. Let me do the other way around. So let x be in bx minus x. Then by assumption, x is not in y. Okay. By b2, there is y in by minus bx such that bx minus x plus y, the union y, is in the base. So let bx prime to be this thing, bx minus x union y. Now, it would be nice if y is in the small y, if small y is in this place, right? If small y is here, then we win because bx minus x, so x is here. So even if I delete x, I still contain all the elements of x. If this is y, then this plus that is a subset of base, so therefore we win. So this plus that is independent. But the problematic case is when this is y, right? So this shows that there's a base containing this and that. So how do we overcome? And that's where we use this assumption. The assumption is, so we try to do something so that intersection of bx and by is maximized. Right? So when we choose bx and by, satisfying this condition, among all possible choices, I'm going to choose bx and by so that their intersection is maximized. Now, bx prime contains x, by contains y, but bx prime intersection by is bigger, strictly bigger than bx intersection by, so that's contradiction. Okay, so that's the proof. All right, because I remove this element and add that, and then bx prime has one more intersection with by, and that's contradiction. All right. So this shows you that B1 and B2 also defines a matroid. All right. Now let me define the rank. Okay, for a set X, which is subset of E, the rank of X, if sometimes rank M of X, be the size of a maximal independent subset of E. So by I3, all maximal independent set subsets, oh no, not E, not X, of X have the same size. So this rank function is well defined, and this is called rank function. Okay, and we write this, or sometimes we just write rank of X. And rank of M is the rank function of this thing. So this is a rank of the matroid M. Okay. So for instance, if M is a vector matroid, right? So you have a matrix. Let me just give an example, right? The columns span, so each column represents one vector. Then rank is the same as what? It's the size of base, but column base. So it's demand, right? It's same as size of a column base. what is it? Rank of the matrix. So that's why we call it a rank. If M is a cycle matroid, if M is cycle matroid of graph G, then what is rank? Well, it's a base. Base is at the independent maximum size. So rank is the maximum size of independent set, and independence means no cycles. So it's a size of a maximal subgraph without cycles. So each component will be a tree. So that's same as number of edges in a spanning tree. But I don't want to say spanning tree. I could say that the union of spanning trees of each component. And that's the number of vertices minus 1. So this is number of vertices. Number of vertices of the graph minus number of components. All right, so that's the rank of the cycle matroid. All right. Now, let me define the fundamental circuit. So, here's a lemma. Let B be a base of M. Let E be the elements, not in B. So here, this notation just means the set of ground. The ground set of the matroid, which is a set of elements in E. I mean, it's the same as E. All right, so then M contains a unique circuit, which is I should say M. B union E contains a unique circuit, and this unique circuit is called the fundamental circuit. Of X with respect to B. Okay, and the proof is quite trivial. So why? First of all, B union E contains circuit because it is independent. It is dependent. B was a maximal independent set, so any superset, any proper superset of B is dependent, so it contains a circuit. So why is it unique? If B union E contains two circuits, CD, then E is in the intersection. Why? Because B does not contain any circuit, so any circuit inside B union E must be there. All right, so now by C3 there is a circuit F, which is a C union D minus E, but F is a subset of B, contradiction. B is base, so it's independent, so independent set that cannot contain any circuit. And what is the fundamental circuit in a graph? So if I have a spanning tree, then have an any edge outside, then this cycle corresponds to the fundamental circuit. And there's a unique cycle. You don't have two cycles. So T plus E has only one cycle, and that is a fundamental cycle. All right. What else? Oh yeah, so we talked about rank function, so maybe it's good to describe the properties of rank function. If R is the rank function of a matroid, then you satisfy three properties. So the first one is rank function has always value between 0 and x, size of x, for all x is a subset of E, and if x is subset of y, then rank of x is subset less than or equal to rank of y, right? And for all xy subsets of for all subsets xy of E, rank of x plus rank of y is at least rank of x union y plus rank of x intersection y. So these are the three properties of the rank functions. And the R3 is commonly called the submodular inequality. Now, why does it satisfy these things? So for instance, R1, well, this is trivial. Why? I mean, it's trivial by the definition. Rank is the size of maximal independent subset of X, right? So it has to be a size of subset. So it's trivial by the definition. What about R2? Why? X contains an independent set of size rank of X, so that means rank of Y has to be at least rank of X. This is by I3 in some sense, because all independent sets, all maximal independent subsets of X, Y have the same size, which is the rank. Now R3. How do we prove the R3? So here's an X, here's a Y. Let I1 be an independent set, subset of X intersection Y of size rank of X intersection Y. So here's the I1. Now let I2 be a maximal independent subset of X union Y containing I1. Right? I mean, I1 is independent, so I can start from I1 and extend it to the maximal independent set. So that's I2. Then by I3, size of R2 is equal, size of I2 is equal to rank of X union Y. Now I2 intersection X and I2 intersection Y are independent. So rank of X is at least size of I2 intersection X. Rank of Y is at least size of I2 intersection Y. But I2 intersection x plus I2 intersection y is equal to right, so that's what I counted twice. This is size of I2 plus people in the intersections are counted twice, so I have to add them, but I1s are counted. So this is rank of x plus rank of y, right? And this is rank of x intersection y plus rank of x union y. So that proves the submodular inequality. All right. Again, now you notice the similar pattern, right? Let R be a function from the subsets of E to the set of non-negative integers. Satisfying R1, R2, R3. Now let I be the set of subsets of E such that rank of X is equal to size of X. So what does that mean? I will call the subset is independent if its rank is equal to size. Then EI is a matroid. Why is this true? What about I1? Rank of empty set is between 0 and empty size of empty set. So rank of empty set is 0, so that means empty set is in I. So that's fine. What about the second one? Suppose y is a subset of x, then rank of y plus rank of x minus y is by the submodular inequality. This is a union and intersection. And I know this is 0. So rank of y plus rank of x minus y is at least rank of x. And I assume that x, y are both independent, so this is no, not both independent. X is independent. And by R1, rank of x minus y is at most x minus y. Right? So rank of y is at least y x minus y, but that's size of y. And by R1, rank of y is less than equal to y, so therefore rank of y is equal to y. So y is independent. So these two properties hold. What about the last one? So suppose x, y are independent sets of different size. All right. Now, x is y. Now, choose a maximal subset S of y minus x. So here's S, such that rank of x union S is equal to rank of size of x. And what will happen? I know the rank of x is equal to x, so S, such a thing, so S exists, right? Because I can take S to be empty, then it satisfies that property. And if rank of x plus one element is bigger than x, for some y in y minus x, then since it's integer values by R1, rank of x union y most x plus 1, and this is bigger than x, so x union y is independent. So then we are done, right? This is what we want. So we may assume rank of x union this is the most size of x, and I knew that it's already this because rank is increasing function by, so this is by R2. So rank of x union y is equal to x for all y in y minus x. Now we claim that s is equal to y minus x. If not, let y be a subset in y minus, an element in y minus s. Okay, y minus x minus s. This is s and this is y. Now rank of x union y is equal to x. Rank of x union s is equal to x. Now by R3 we can apply some modular inequality. This is x union s union y, and the intersection is rank of x. Now let's see, this is equal to x, and this is equal to sides of x, this is equal to sides of x. So this implies that rank of x union s union y is at most sides of s, but I knew already that this is x by R2. So this means rank of x union s union y is equal to x. Contradiction to the assumption that x is chosen to be maximal. So s is equal to y minus x. So the rank of x union s is equal to rank of equal to x, which is rank of x union y. But that's strange. That's bigger than rank of y by R2, and this is equal to rank of y. So x is bigger than y. Contradiction. Okay, all right. So far we so far we showed many equivalent definitions of matroid. All of them are equivalent. You can define matroid in terms of independent sets, in terms of circuits, in terms of bases, in terms of rank functions. And depending on the context, we're going to choose good ones. And there are much more interesting definitions. But for our course, we will stop here. Okay, and in the next lecture, we will talk about more properties of matroid. Okay.